Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the Chinese remainder theorem. So this is going to involve solving equations modulo n. So let's have a quick introduction to that. So I've got two equations here. 4x is equivalent to 5 mod 8. 4x is equivalent to 5 mod 9. So we learned in a previous lesson about inverses. The significance of a multiplicative inverse is that you can undo multiplication. You can cancel. See, 4 is co-prime to 9. So I know that 4 has a multiplicative inverse modulo 9. The inverse of 4 modulo 9 is equal to 7. The reason being 4 times 7 is 28, which is equivalent to 1 mod 9. So I can solve this equation by multiplying each side by 7, because 7 times 4 is just 1 modulo 9. So I end up with just x equals 5 times 7 is 35, which is of course equivalent to 8 mod 9. So I was able to solve this equation because 4 has an inverse modulo 9, because I am able to undo multiplying by 4. You actually undo multiplying by 4 by multiplying by 7 modulo 9. But this equation here doesn't have a solution, and you can probably see that. Yet 4x, 4 times an integer, is always going to be even, and an even integer can't be equivalent to 5 mod 8, because 5 mod 8 is always going to be odd. So this one here has no solution. How do I know whether or not it has a solution? Well, here, 4 and 8 are not co-prime. Their highest common factor is 4. Consequently, 4 does not have a multiplicative inverse modulo 8. It definitely has an additive inverse, which is itself, but because 4 doesn't have a multiplicative inverse modulo 8, I can't divide by 4. In other words, I can't undo multiplying by 4. So it turns out there will be a solution to an equation like this if these are co-prime. So we're now going to look at solving many of these simultaneously, for which we'll use the Chinese remainder theorem. So the Chinese remainder theorem tells us that if you have congruences like this that you want to solve at the same time, there will be a unique solution modulo a times b as long as a and b are co-prime to each other. That will allow us to avoid a situation like we saw in the previous slide. So if I wanted to solve x is equivalent to 1 mod 4 and x is equivalent to 2 mod 10, I actually can't do it. There's no solution. Once again, anything equivalent to 1 mod 4 must be odd. Anything equivalent to 2 mod 10 is even. So I will never be able to find a value for x that satisfies both of these equations at the same time. So the reason it doesn't work here is 4 and 10 are not co-prime. So the Chinese remainder theorem doesn't guarantee that there will be a solution. So let's look at the Chinese remainder theorem in action. So let's say I have a bag of coins. If placed in groups of 4, I have 3 left over. If placed in groups of 9, I have 1 left over. If placed in groups of 13, I have none left over. How many coins must I have? So what we're essentially doing here is we are solving this system of linear congruences. I want to find a number that is equivalent to 3 mod 4. That's what it means by when I divide by 4, there are 3 left over. And similarly, I want to solve x is equivalent to 1 mod 9 and 0 mod 13. I want to find a value of x that satisfies each of these congruences simultaneously at the same time. So how do I do that? Now notice that any number that's equivalent to 3 mod 4 can be written in the form as 4k plus 3, where k is an integer. So 3 more than a multiple of 4. So what I want is I want this integer that's 4 mod 3 to be equivalent to 1 mod 9. So what I'm going to do is subtract 3 from both sides. So notice that negative 2 mod 9, if I add another 9, I get 7. Negative 2 and 7 are congruent in mod 9. So on the previous slide, remember we figured out that the inverse of 4 modulo 9 is 7. So I can just multiply each side by 7. The reason I'm multiplying by 7 is because 7 and 4 are inverses, are multiplicative inverses modulo 9. So then I'll just be left with k is equivalent to 49, which is equivalent to 4 mod 9. So I found first that x was going to be of the form 4k plus 3. But I've just found from this equation, I also want it to be of the form 9k plus 4. 4 more than a multiple of 9. So I'm going to replace this k here with 9k plus 4. So expanding the brackets and simplifying, I get 36k plus 19. So any number of this form will satisfy the first two. It will be 1 more than a multiple of 9. It will be 3 more than a multiple of 4. But I also want this to be equivalent to 0 mod 13. So I'm going to solve this equal to 0 mod 13. So to solve this equation, I'm going to subtract 19 from both sides. So notice negative 19 plus 13 plus 13. Negative 19 is the same as 7 mod 13. So I'm solving 36k is equivalent to 7 mod 13. So what's the inverse of 36 mod 13? Well, 36 is the same as 10 mod 13. So the inverse of 10 mod 13 is 4, because 10 times 4, 40, is equivalent to 1 mod 13. So what I'm going to do is I'm going to multiply each side by 4. So what I get here, 4 times 36 is equivalent to 1 mod 13. So I get k by itself. 7 times 4 is 28, so that gives me 2 mod 13. So I found out before I want my integer x to be of the form 36k plus 19, but I also want it to be now of the form 13k plus 2. So what I'm going to do is I'm going to take my k and I'm going to replace it with 2 mod 13, or 13k plus 2. So here I've just replaced k with 13k plus 2. Expanding that, I have 468k plus 91. So what have I actually found here? So I've found that a number will be equivalent to 3 mod 4, also equivalent to 1 mod 9, also equivalent to 0 mod 13, if it is of the form 468k plus 91, where k is an integer. So how many coins must I have? Well, there are infinitely many solutions. I could have 91. If k is equal to 1, I would have 559. If k was equal to 2, I'd have 1,027, and so on. So each of those numbers, 91, 559, 1,027, satisfies each of these equations at the same time. So that's how many coins I could have. 91, 559, 1,027, and so on. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.